Hello there, and welcome to The Whispering Scientist. I'm so glad you found your way here tonight, to this quiet corner where curiosity meets calm, where the impossible becomes a gentle lullaby. Whether you're nestled under familiar blankets, listening while the world outside settles into stillness, or simply letting your mind float like dandelion seeds on a warm evening breeze, this is your invitation to drift into something extraordinary. Tonight, we're stepping through a doorway into the quantum dream, a realm so beautifully strange it might just convince you that reality itself is far more magical than you ever imagined. Before we begin our gentle journey, I have a small confession. I do hope this exploration won't be too fascinating. That's always the delicate balance with quantum mechanics, you see. It has this tendency to be absolutely captivating, and we wouldn't want to keep you awake when what we really want is for your eyelids to grow heavy as electrons settle into their probability clouds. But with our unhurried pace and soft whispers, perhaps your mind will find that perfect space between wonder and rest. I'd love to know, where in the world are you listening tonight? What time is it in your cozy corner of the cosmos? Drop a comment below and let me know. I always find such joy in discovering where these quantum whispers are keeping people company. And if you find yourself enjoying this soft adventure into the impossible, please consider giving this video a gentle like and perhaps subscribe to join our community of curious dreamers. One gentle reminder before we dive deeper. This journey is designed for relaxation, curiosity, and bedtime wonder. It's not medical advice nor a substitute for professional care. Always speak with qualified health providers for any concerns about your sleep or well-being. Now, let your breathing slow, let your shoulders drop, and imagine you're standing in a room with the lights off, holding a lantern that throws a small circle of glow ahead of you. In our everyday world, you know the furniture is there whether you shine the light on it or not, just waiting to be seen. You set a cup on a table. It stays put. A ball arcs through the air in a curve your body understands without doing any math. We call this classical physics, the familiar choreography of objects that seem solid and certain. But now set the lantern aside and imagine something smaller than dust, smaller than the smallest thing you've ever seen, something like an electron. Instead of being a little pebble sitting in one spot, it's more like a patch of mist. Not here or there, but here-ish and there-ish. A soft cloud of possibilities gathered loosely in space. When you look closely, when you measure, it chooses a spot like mist, becoming a drop on the window. When you stop looking, it returns to its gentle indecision. This is the heart of quantum physics, this beautiful realm of invisible poetry written in a language of probability and possibility. Picture a set of keys you left somewhere. In the ordinary story, they're in one place, and you simply haven't found them yet. In the quantum story, before you look, they're genuinely spread across possibilities, the hallway table, the coat pocket, the kitchen drawer, all at once in a delicate overlap. Only when you reach out do they commit, and the kitchen drawer becomes the place they always were, as if the other options slide quietly out of the narrative. Now imagine a coin flicked into the air and frozen. Not in a photograph, but in a held breath between outcomes. Not heads, not tails, but a poised shimmer that contains both futures at once. The rules of the small allow such poise. They prefer it, in fact, until a question is asked, until reality is invited to make a choice. This is what we call superposition, and it's not indecision, it's a kind of generosity. Instead of forcing one path, the universe keeps options open and then, when touched, writes a single line. The mathematical framework that supports this idea is surprisingly precise, even if the concept feels wonderfully hazy. We use something called a wave function, a mathematical expression that describes the probabilities of where a particle might be and what it might be doing. It's like a cosmic weather forecast, but instead of predicting rain, it predicts where an electron might decide to materialize when you take a peek. And unlike many weather forecasts, quantum predictions are astonishingly accurate, matching reality with uncanny precision. Even Einstein found this unsettling. He famously quipped, God does not play dice with the universe. To which the pioneering quantum physicist Niels Bohr essentially replied, "Einstein, stop telling God what to do." Yet the miracle is that even though quantum behavior is full of probabilities, the large-scale world emerges from it with remarkable stability. Billions of quantum maybes somehow add up to one very real table that doesn't suddenly vanish while you're sipping your tea. And what about the fear that all this uncertainty means chaos? Let that go gently. The quantum world is meticulously consistent in a way that leaves very little room for mischief. The maybes come with honest probabilities that repeat so reliably, we've built the devices you're using right now on their promises. Every chemical reaction in your body, every flicker of electricity in your brain, every beam of starlight is governed by these quantum rules. You are made of quantum stuff, and perhaps that's not so strange after all, so let the room be quiet. Let your curiosity bloom like a night flower as we prepare to meet these quantum performers one by one. In the next breath, we'll discover how particles can dance in more than one place at once, and we'll give that poised shimmer its true and beautiful name. On that next gentle breath, let's give our poised shimmer its true name and watch it unfold like a night flower, opening to starlight. Superposition. The word itself sounds like a lullaby whispered to the quantum world, and in many ways it is. This is nature's way of saying not yet to the universe's questions, of holding multiple stories in the same breath until someone asks which one is real. Imagine that coin we left spinning in the air, suspended in that perfect moment between outcomes. In our everyday world, we know it must be either heads or tails, even if we can't see it clearly. We assume it is already decided and we simply haven't discovered its secret yet. But in the quantum realm, that spinning coin genuinely carries both possibilities at once, not as uncertainty in our minds, but as a real physical state that contains both futures woven together like harmonies in a chord. When the coin finally lands, when observation gently asks for an answer, you hear just one clear note, heads or tails, while the other possibility fades like music that was always there, but never meant to be heard alone. Let's return to our familiar electron, that tiny performer on the quantum stage. It possesses something called spin, though not the spinning of a child's top. Think of it more as an intrinsic compass that can point either up or down when we choose to measure it along a particular direction. But here's where quantum magic reveals itself. Before we measure, the electron doesn't secretly hold one direction or the other, waiting for us to discover its hidden truth. Instead, it exists in a superposition of both spin up and spin down simultaneously, a mathematical embrace that combines both possibilities into something entirely new. The wave function we touched on earlier doesn't describe our ignorance about which state the electron is in. It describes a genuine physical reality that encompasses both possibilities, weighted by complex numbers that determine the likelihood of each outcome when we finally decide to look. It's not that we don't know which it is. It's that it truly is both, held in a delicate quantum poise until the moment measurement asks it to choose. This brings us to one of the most famous residents of the quantum world, though perhaps the most misunderstood. In the 1930s, physicist Erwin Schrödinger proposed a thought experiment involving a cat sealed in a box, connected through an elaborate mechanism to a single radioactive atom with a 50% chance of decaying. If the atom decays, poison is released and the cat dies. If not, the cat lives. Since the quantum atom exists in superposition, both decayed and not decayed, Schrödinger suggested that the cat, too, must be in superposition, both alive and dead, simultaneously. But here's the gentle truth often lost in the telling. Schrödinger wasn't celebrating this idea. He was showing how strange it would be to apply quantum principles to everyday objects. The cat, of course, never actually exists in superposition. It's constantly breathing, moving, interacting with air molecules and photons, existing in a world of continuous measurement that keeps it firmly in the realm of being definitively alive or dead. The thought experiment serves as a bridge, showing us where the quantum world of electrons meets our classical world of cats and coffee cups. This boundary exists because superposition is remarkably delicate, like a whisper that survives in a quiet library but dissolves in a bustling marketplace. The moment a quantum system interacts with its environment, with the gentle brush of an air molecule or the touch of a stray photon, the pristine superposition begins to unravel. Physicists call this decoherence, and for large objects like cats or tables, it happens so quickly that superposition vanishes before it can properly form. But for tiny, isolated particles protected from the noise of the world, superposition can persist, creating spaces where the impossible becomes routine. This fragility is both a challenge and a gift. It makes quantum computers extraordinarily difficult to build because their quantum bits, their qubits, must maintain superposition long enough to perform calculations. But it also makes superposition precious, like soap bubbles that exist only in perfect balance, beautiful precisely because they're ephemeral. In quantum computers, these qubits don't just store 0 or 1 like classical bits. They can exist as both 0 and 1 simultaneously, like that spinning coin holding all possibilities in play at once. With many qubits working together, a quantum computer can explore vast landscapes of solutions all at once, walking multiple paths through a maze simultaneously rather than trying each route one at a time. As you lie there, perhaps noticing how your own consciousness hovers between wakefulness and sleep, consider that you're witnessing your own version of this dance between possibilities. Not quantum superposition, but something equally mysterious, the way awareness can exist in multiple states at once, alert and dreamy, focused and drifting. Your thoughts seem to float between options before settling into words, much like particles existing in superposition before collapsing into definite states when observed. Superposition isn't confusion or cosmic indecision. It's a fundamental way of being that recognizes reality at its deepest level is richer than our everyday experience suggests. It's nature's way of keeping doors open, of refusing to be pinned down until absolutely necessary. In that gentle refusal, in that insistence on remaining possible rather than actual, there's something profoundly hopeful, a reminder that the universe prefers abundance to limitation, potential to certainty. So let your mind rest in that space of possibility as we prepare to witness what happens when this dance meets one of physics' most elegant demonstrations. We'll dim the lights a little more and set up a simple stage, a source of particles, a barrier with 2 narrow openings, and a screen to catch whatever arrives. Nothing dramatic, just a quiet arrangement that will invite superposition to draw its own portrait in light and shadow, showing us how a single particle can walk 2 paths at once and meet itself where they cross. Now let's dim the lights just a little more and arrange our quiet stage where superposition will paint its own portrait, showing us how that spinning coin we imagined can actually draw pictures with light and shadow. Picture a simple theatre, a gentle source sending out our familiar electrons one by one, a thin wall standing before us with 2 narrow doorways cut through it like windows, barely wide enough for possibility to slip through. And behind this barrier, a patient screen waiting to catch whatever manages to pass through our twin openings. There's nothing elaborate here, no complex machinery, just particles, barriers, and a canvas where the universe will sketch its deepest secret. We begin gently, as all good experiments should. Let's close the right doorway and leave only the left one open, sending our electrons toward the wall like soft raindrops approaching a window with a single opening. On our screen, a simple stripe appears, aligned perfectly with the open slit, exactly as you'd expect if you were tossing pebbles through a single hole in a fence. Close that slit and open the other, and another neat stripe appears, shifted to match the new opening. 1 path, 1 stripe. It feels as straightforward as breathing. Nothing here to disturb your gentle drift towards sleep. But now comes the moment that has been quietly revolutionizing our understanding of reality for over a century. We open both doorways at once and send our electrons toward the wall. Logic whispers that we should see both stripes together, a simple combination of the two patterns we observed before. After all, each electron must choose one door or the other, mustn't it? There seems to be no other possibility our everyday minds can imagine. Yet what appears on our screen speaks in an entirely different language. Instead of two neat stripes, we see a series of alternating bright and dark bands stretching across the screen, a zebra pattern of light and shadow that physicists call an interference pattern. This is the signature of waves meeting waves, where peaks align with peaks to create brightness, and peaks meet valleys to cancel into darkness. But we're sending particles, tiny discrete electrons. How can particles create the poetry of waves? The answer drifts to us from our earlier conversation about superposition. When both slits are open, each electron doesn't choose a path through one opening or the other. Instead, it exists in that beautiful state we explored, encompassing both possibilities simultaneously. The electron's wave function spreads like ripples on a quiet pond, flowing through both doorways at once, and then these twin streams of possibility interfere with each other downstream, creating the pattern before the electron finally chooses where to land. Let's make this even more quietly mysterious. We can slow our experiment down, sending electrons one at a time with long, peaceful pauses between them, ensuring that each traveler journeys alone through our apparatus. There are no other electrons to bump into, no crowd to create patterns with, just solitary particles arriving like individual snowflakes. Yet still, as these lonely dots accumulate on our screen, the same zebra stripes emerge. Each electron somehow knows about both doorways, somehow explores both openings, somehow interferes with its own possibilities before settling into a single point of arrival. It's as if each electron carries within itself a quiet conversation with all the paths it might have taken, a whispered dialogue between what could be and what will be. The wave function we discussed earlier isn't describing our ignorance about which path the electron chose. It's describing a genuine physical reality where the electron genuinely travels both paths, until the moment it meets our screen and must commit to being in one specific place. But here's where the quantum world offers us its most profound surprise. What happens if we become curious about which doorway each electron actually uses? What if we place gentle detectors near the openings just to peek and see which path each electron chooses? The moment we do this, the moment we ask the universe to reveal its secret, something remarkable occurs. The interference pattern vanishes like morning mist touched by sunlight. Those beautiful zebra stripes disappear, replaced by exactly what our classical intuition expected from the beginning. Two simple stripes, one aligned with each doorway. The act of looking itself changes the story. When we don't observe the path, the electron behaves like a wave, exploring both routes simultaneously and interfering with itself to create that delicate pattern. When we do look, when we gather information about which slit it used, the electron behaves like a particle, choosing one definite path and abandoning its quantum ambiguity. It's not that our detector is clumsy or that we're disturbing the electron physically. Even the gentlest, most indirect methods of gaining path information cause the interference to dissolve. This isn't a limitation of our instruments or a flaw in our understanding. This is how reality works at its deepest level. The universe seems to know when we're watching and adjusts its behavior accordingly, not out of shyness. But because observation and reality are partners in a dance, we're only beginning to understand. As you rest there, perhaps noticing how your own awareness hovers between focus and drift, consider this gentle truth. The double-slit experiment suggests that reality is not made of fixed facts waiting to be discovered, but of relationships between observer and observed, between question and answer. The electron's path doesn't exist as a definite fact until someone asks about it. Until then, it exists as pure potential, that superposition of possibilities we met earlier, crystallizing into a single story only when touched by curiosity. This dance between wave and particle, between potential and actual, between mystery and measurement, leads us naturally toward our next quiet revelation. For if the very act of observation shapes what we observe, then we must gently ask, what else about reality might be fundamentally uncertain? What other truths might exist in that soft space between knowing and not knowing? Let your breathing slow as we prepare to meet uncertainty itself, not as a flaw in our knowledge, but as a feature woven into the very fabric of existence. Let that question rest gently on your mind as we drift from the double slits revelation into something even more profound. We've seen how the simple act of looking changes the story a particle tells, transforming wave into particle, possibility into certainty. But this dance between observer and observed whispers of something deeper, a truth that touches the very heart of what it means to know anything at all. If reality responds to our questions, reshaping itself based on what we choose to ask, then perhaps there are limits to what questions we can ask simultaneously. Imagine yourself in a moonlit garden, trying to photograph a delicate firefly as it dances through the darkness. To capture exactly where it is, you must shine a light upon it, but that very light startles the tiny creature and sends it fluttering in a new direction. You've pinpointed its location for one perfect moment, but you've lost track of its motion. Alternatively, you could dim your light and watch patiently, following the graceful loops and spirals of its flight, understanding its movement but losing precision about exactly where it hovers at any given instant. The more clearly you define one truth, the more the other dissolves into gentle uncertainty. This is the everyday poetry of what Werner Heisenberg discovered in the late 1920s, a principle so fundamental it reshapes our understanding of knowledge itself. The uncertainty principle tells us that certain pairs of properties in the quantum world cannot both be known with perfect precision at the same time. Position and momentum, those seemingly innocent questions of where something is and how fast it's moving, exist in a delicate tension with each other. The more precisely we determine one, the more uncertain the other becomes, not because our instruments are clumsy or our techniques inadequate, but because uncertainty is woven into the very fabric of reality. In our daily world, this seems absurd. You can watch a bird fly past your window and confidently know both where it is and how fast it's traveling. But shrink that bird down to the size of an electron and something remarkable happens. To see where such a tiny particle is, you must bounce light off it, but light carries energy, and at the quantum scale, even a single photon delivers a significant push. It's like trying to measure the position of a soap bubble by gently tossing pebbles at it. The very act of gaining information about location inevitably disturbs the motion, and vice versa. But here's the beautiful truth that Heisenberg revealed. This isn't a flaw in our measurement techniques. It's a statement about the nature of existence itself. Think of a pure musical note ringing from a tuning fork, sustained and clear. Because it lasts for a long time, its frequency becomes perfectly defined, a single crystalline pitch. But strike that fork and immediately muffle it, creating only the briefest sound, and that note becomes less defined, spreading across a range of frequencies like watercolors bleeding into wet paper. The more precisely you define when the note occurs, the less precisely you can say what note it actually is. Time and frequency, like position and momentum, dance this same delicate waltz of mutual uncertainty. This gentle impossibility of perfect knowledge isn't chaos or randomness as we usually imagine them. It's structured, predictable, mathematically precise uncertainty. We can calculate exactly how uncertain things will be, which is itself a strange kind of certainty. The universe doesn't abandon us to complete mystery, but it does maintain careful boundaries around what can be known simultaneously, ensuring that some questions remain forever paired in their indeterminacy. Consider what this means for the very atoms that compose your resting body. Electrons orbiting atomic nuclei cannot simply spiral inward and collapse, not because of some invisible force field, but because of uncertainty itself. If an electron were to fall into the nucleus, its position would become extremely well defined, confined to that tiny space. The uncertainty principle would then demand that its momentum become wildly uncertain, requiring enormous kinetic energy that would blast the electron back outward. Atoms maintain their size and structure not despite uncertainty, but because of it. The soft edges around quantum facts literally hold the world together. This principle extends beyond position and momentum into other paired mysteries. Energy and time share this same relationship, allowing the universe to briefly borrow energy from nowhere, creating virtual particles that exist for the smallest possible moments before paying back their energetic debt and vanishing. These ghostly fluctuations, born from uncertainty itself, mediate the forces that bind matter together and push it apart as you lie there, perhaps noticing how your own awareness seems to hover between sharp focus and gentle drift. Consider that uncertainty isn't something to be solved or overcome. It's a feature of existence as fundamental as space or time. The universe doesn't just allow for mystery, it requires it. There are questions that cannot be answered, not because we lack sufficient cleverness or powerful enough instruments, but because the questions themselves reshape the reality they attempt to examine. This isn't a limitation that frustrates scientists. It's a revelation that transforms how we understand knowledge itself. The universe is not a collection of fixed facts waiting to be discovered like treasures in a vault. Instead, it's a dynamic conversation between observer and observed, between question and answer, where the very act of inquiry participates in creating the reality we seek to understand. Now, you might wonder if this uncertainty is noticeable in your everyday experience. The answer is both no and yes. The numbers involved are so incredibly tiny that for objects larger than molecules, the fuzziness becomes imperceptible. But at the quantum scale, uncertainty reigns supreme, defining what can and cannot be known, drawing soft curtains between possibility and measurement. Some find this unsettling, this loss of perfect knowledge, this recognition that we live in a universe with built-in boundaries around certainty. But there's another way to see it. The uncertainty principle is also a gentle invitation to release the need for total precision, to understand that even at the most fundamental level, nature allows room for flexibility, for openness, for the beautifully indeterminate. It reminds us that the world is not rigid but breathes, shimmers, and dances between being and becoming. And perhaps that's the most comforting truth of all, that even reality at its deepest level has a softness to it, a blur, a breath, a margin of mystery. This mystery is not a flaw but a feature, not an obstacle but an opening into something even more extraordinary. For if individual particles live in this soft space between certainty and uncertainty, what happens when particles become intimately connected, when their uncertainties become shared across vast distances? Let your breathing deepen as we prepare to explore invisible threads that connect separated things, relationships that Einstein himself called spooky, and the strange ways that the universe weaves connection from the very fabric of uncertainty itself. Let that question about observation changing reality settle gently in your awareness as we follow its implications into something even more profound. We've discovered that the simple act of looking transforms waves into particles, possibility into certainty. But this dance between observer and observed whispers of deeper mysteries. If reality reshapes itself based on our questions, perhaps there are fundamental limits to what questions we can ask simultaneously, boundaries written into the very fabric of existence itself. Imagine yourself in a moonlit garden, trying to photograph a delicate firefly as it dances through the darkness. To capture exactly where it hovers, you must shine a light upon it, but that very illumination startles the tiny creature, sending it fluttering in a new direction. You've pinpointed its location for one perfect moment, but you've lost all the knowledge of where it was heading. Alternatively, you could dim your light and watch patiently, following the graceful loops and spirals of its flight path, understanding its motion but losing precision about exactly where it pauses at any given instant. The more clearly you define one truth, the more the other dissolves into gentle uncertainty. This everyday poetry captures what Werner Heisenberg discovered in the late 1920s, a principle so fundamental it reshapes our understanding of knowledge itself. The uncertainty principle reveals that certain pairs of properties cannot both be known with perfect precision simultaneously. Position and momentum, those seemingly innocent questions of where something is and how fast it's moving, exist in delicate tension with each other. The more precisely we determine one, the more uncertain the other becomes, not because our instruments lack sophistication, but because uncertainty is woven into reality's deepest patterns. Consider a pure musical note ringing from a tuning fork, sustained and crystalline. Because it lasts for a long time, its frequency becomes perfectly defined, a single, clear pitch. But strike that fork and immediately muffle it, creating only the briefest sound, and that note becomes less defined, spreading across frequencies like watercolors bleeding into wet paper. The more precisely you confine when the note occurs, the less precisely you can say what note it actually is. Time and frequency dance the same delicate waltz of mutual uncertainty that governs position and momentum. This isn't chaos or randomness as we usually imagine them. It's structured, mathematically precise uncertainty. We can calculate exactly how uncertain things will be, which is itself a strange kind of certainty. The universe doesn't abandon us to complete mystery, but it does maintain careful boundaries around simultaneous knowledge, ensuring that some questions remain forever paired in their beautiful indeterminacy. Think of what this means for the very atoms composing your resting body. Electrons cannot simply spiral inward and collapse into atomic nuclei, not because of invisible barriers, but because of uncertainty itself. If an electron were confined to that tiny nucleus space, its position would become extremely well defined. The uncertainty principle would then demand that its momentum become wildly uncertain, requiring enormous kinetic energy that would blast the electron back outward. Atoms maintain their size and structure not despite uncertainty, but because of it. The soft edges around quantum facts literally hold the world together. This principle extends beyond position and momentum into other paired mysteries. Energy and time share this same relationship, allowing the universe to briefly borrow energy from nowhere, creating virtual particles that exist for the smallest possible moments before returning their energetic debt and vanishing. These ghostly fluctuations, born from uncertainty itself, mediate the forces that bind and separate all matter. As you lie there, perhaps noticing how your own awareness hovers between sharp focus and gentle drift, consider that uncertainty isn't something to be solved or overcome. It's a feature of existence as fundamental as space or time. The universe doesn't just allow mystery, it requires it. There are questions that cannot be answered, not because we lack cleverness or powerful enough instruments, but because the questions themselves participate in shaping the reality they attempt to examine. This recognition transforms how we understand knowledge itself. The universe is not a vault of fixed facts waiting to be discovered, but a dynamic conversation between observer and observed, between question and answer, where inquiry participates in creating the reality we seek to understand. Some find this loss of perfect knowledge unsettling, but there's another way to see it. The uncertainty principle is a gentle invitation to release the need for total precision, to understand that even at the most fundamental level, nature allows room for flexibility, openness, and the beautifully indeterminate. And perhaps that's the most comforting truth of all. Even reality at its deepest level has a softness to it, a breath, a margin of mystery that is not flaw but feature, not obstacle but opening. For if individual particles must live with these soft boundaries around what can be known, what happens when particles become intimately connected? What occurs when their uncertainties become shared across vast distances, when the gentle indeterminacy we've discovered becomes the foundation for connections that stretch across space itself? Let your breathing deepen as we prepare to explore invisible threads that bind separated things, relationships so profound that Einstein himself called them spooky, and the extraordinary ways that uncertainty itself becomes the medium through which the universe weaves connection from the very fabric of quantum possibility. In the space between one breath and the next, we'll discover how two particles can share a single quantum story, no matter how far apart their chapters unfold. Let that question about shared uncertainties across vast distances rest gently in your awareness as we follow one more delicate thread. We've discovered how the universe maintains soft boundaries around simultaneous knowledge, how the more precisely we pin down one truth, the more another dissolves into beautiful indeterminacy. But this dance between certainty and uncertainty whispers of something even more fundamental. What does it mean to ask a question of reality at all? What happens in that gentle moment when we reach out with our instruments and curiosity to touch the quantum world? Picture yourself walking through a moonlit forest carrying a lantern to light your way. In the soft glow ahead, you glimpse a deer standing motionless between the trees. To see it more clearly, you raise your lantern higher, but the sudden brightness startles the creature and it bounds away into the darkness. You've learned where the deer was, but your very act of looking has changed what it does next. In our everyday world, this seems like a minor inconvenience, a small price to pay for knowledge. But in the quantum realm, this interaction between observer and observed becomes the very foundation of reality itself. This is the observer effect, one of the most profound and gently unsettling truths of quantum mechanics. It tells us that the act of measurement doesn't simply reveal what a quantum system is doing. It fundamentally changes what the system is doing. Observation is never passive in the quantum world. It's always participation, like trying to measure the shape of a soap bubble by touching it with your finger. The very gentleness required to gather information inevitably alters the delicate thing you're trying to understand. At the quantum level, this isn't just about physical disturbance, though that plays a role. To determine where an electron is, we must bounce photons off it, and those photons carry energy that nudges the electron, changing its momentum. This is one reason why the uncertainty principle we just explored exists, why position and momentum cannot both be known with perfect precision. But the observer effect runs deeper than this mechanical pushing and shoving. Quantum theory whispers an even stranger truth. The properties we measure often don't exist as definite facts until we measure them. Before observation, an electron's position isn't hidden in some secret location waiting to be discovered. Instead, it exists as a wave function, a mathematical description of all possible positions weighted by their probabilities. The electron genuinely occupies a superposition of locations, that beautiful state of being many things at once that we've been gently exploring. When we choose to measure the electron's position, something remarkable happens. The wave function collapses, narrowing from a spread of possibilities into a single, definite outcome. It's as if the universe has been writing a story in pencil, keeping many possible endings alive simultaneously, and our measurement acts as an eraser, removing all possibilities except one. Before we look, the electron might be here, there, or anywhere in between. After we measure, all that potential crystallizes into one sharp, undeniable fact. This raises a question that has sparked countless late-night conversations among physicists and philosophers. What exactly counts as an observation? Does it require human consciousness, a scientist in a laboratory coat peering through instruments? Some early quantum pioneers wondered whether the mind itself might be necessary to collapse wave functions, whether reality remains suspended in superposition until a conscious observer forces it to choose. It's a captivating idea, one that tickles the boundaries between science and philosophy. But most physicists today embrace a gentler explanation. Consciousness isn't required for wave function collapse. Instead, any irreversible interaction with the environment can serve as a measurement. This process, called decoherence, occurs when a delicate quantum system becomes entangled with the countless particles and forces surrounding it. Imagine a drop of ink placed in perfectly still water, maintaining its coherent shape and color. But the moment the water is stirred, the ink spreads and dissipates, losing its distinct identity as it mingles with the whole. Decoherence is like stirring. When a quantum system interacts with air molecules, stray photons, or the atoms in a measuring device, its pristine superposition spreads into the environment like ink, bleeding into water. The clean mathematical wave function breaks down, and the system begins behaving like a classical object with definite properties. This is why cats, chairs, and the moon don't exist in superposition. They're constantly interacting with their surroundings, continuously measured by countless environmental factors that collapse any potential quantum indeterminacy long before human observers enter the picture. You can rest peacefully knowing the moon remains in its orbit even when no one is gazing upward. But for tiny particles carefully isolated from environmental noise, the story is beautifully different. They can maintain their quantum superposition, existing in that shimmering space between possibilities until something asks them to choose. And here's the profound truth that emerges. When we observe something in the quantum world, we're not just gathering neutral information. We're participating in a conversation between question and answer, between curiosity and reality. Think about this for a moment. Each measurement you make shapes the story the universe tells. You're not standing outside reality looking in. You're woven into its fabric as both observer and participant, actor and audience. Your questions carve reality into answerable slices, selecting which aspects can be known while leaving others to float in gentle uncertainty. This doesn't mean you're creating reality with your thoughts, or that consciousness controls quantum mechanics. But it does mean that the act of inquiry participates in shaping what can be discovered. Reality isn't a collection of fixed facts waiting patiently to be uncovered like treasures in a vault. Instead, it's a dynamic conversation where the questions we ask help determine the answers we can receive. As you lie there, half in thought and half in dream, consider this beautiful truth. Every photon, every electron, every quantum particle exists in a realm of possibility until something reaches out to touch it with curiosity. And when that touch comes, when observation gently asks reality to commit to an answer, you're witnessing the universe write itself into existence, one measurement at a time. This understanding of observation as participation, of measurement as conversation, prepares us perfectly for our next gentle revelation. For if particles can exist in superposition until observed, if reality emerges from the interaction between the question and quantum system, then what lies beneath it all? What is the invisible stage upon which these quantum dramas unfold? Let your breathing deepen as we prepare to dive beneath the surface of particles themselves, into the vast ocean of quantum fields that fills every corner of space, where particles are revealed to be not objects at all, but gentle ripples in something far more fundamental and beautifully strange. I notice there may be a small sequencing consideration here. Based on the narrative flow we've established, where Chapter 6 ended with exploring invisible threads that connect separated things and spooky action at a distance, the logical next step would typically be Chapter 5, Quantum Entanglement. However, I'll provide Chapter 7 as requested, ensuring it flows smoothly from the observer effect discussion. Let that understanding of observation as participation, of measurement as conversation between curiosity and reality, settle gently into your awareness as we dive deeper still. Beneath the surface of particles themselves, we've discovered that the simple act of looking transforms possibility into certainty, that reality emerges from the delicate interaction between question and quantum system. But this raises a profound question that whispers at the edges of our understanding. If particles can exist in superposition until observed, if they respond to our measurements by choosing definite states, Then what lies beneath it all? What is the invisible stage upon which these quantum conversations unfold? Picture the universe not as a collection of tiny, separate objects floating through empty space, but as a vast, boundless ocean. Not an ocean of water, but of invisible energy fields stretching through every corner of existence, filling what we mistakenly call the vacuum with invisible presence. In this serene, infinite sea, gentle ripples form. These aren't caused by wind or stones cast from above, but by tiny excitations of the fields themselves. And those ripples, those brief, localized disturbances traveling across the field's surface, are what we experience as particles: the electron, the photon, the quark, every fundamental building block of reality. This is the heart of quantum field theory, a vision so elegant it transforms our entire understanding of existence. Fields come first, permeating all of space like water, filling every corner of a vast container. Particles are simply what happens when you gently stir these fields, creating localized waves that carry energy and momentum as they propagate through the medium that birthed them. When we observe an electron, we're not seeing a tiny sphere traveling through emptiness. We're witnessing a small, concentrated ripple in the electron field, a field that extends throughout the entire universe. Imagine dropping a pebble into a perfectly calm lake at dawn. Concentric circles spread outward from the point of impact, ripples moving across the surface in mathematical harmony. Those ripples aren't separate from the lake. They are the lake expressing its capacity for motion, the lake temporarily gathered into traveling patterns of disturbance. This is how particles relate to their fields. The electron isn't riding on the electron field like a surfer on a wave. It is the field momentarily concentrated into a form we can measure and observe. This perspective explains something that has always seemed mysterious: why every electron in the universe is exactly identical. If electrons were separate, independent objects manufactured in cosmic factories, we might expect subtle differences between them. But if every electron is simply the same kind of ripple on the same underlying field, then they must share identical properties, just as every wave on a pond is made of the same water, following the same fluid dynamics. But here's where the story becomes even more quietly extraordinary. Even when these fields appear perfectly calm, even in what we call empty space, they're never truly still. The uncertainty principle we explored earlier extends to the fields themselves, meaning they cannot remain motionless even in their lowest energy states. Instead, they fluctuate constantly, twitching and shimmering with spontaneous activity that creates brief, ghostly disturbances throughout the vacuum. These fluctuations give birth to virtual particles, though the name might mislead you into thinking they're somehow imaginary. Virtual particles are profoundly real in their effects, even though they exist too briefly to be directly observed. Think of them as the universe's way of borrowing energy from the future, creating momentary pairs of particles and antiparticles before repaying the energetic debt and vanishing back into apparent emptiness. The shorter the borrowed time, the more energy can be temporarily manifested, like a cosmic banking system operating on quantum credit. When two electrons repel each other, they're not touching like billiard balls or connected by invisible strings. Instead, they exchange virtual photons, ephemeral messengers that carry the electromagnetic force between them without ever existing long enough to be caught in flight. These virtual photons don't follow the same rules as the real photons we see as light. They can have impossible properties, carrying messages faster than light should allow, existing for briefer moments than their energy should permit, operating in the shadowy spaces between measurement and reality. This hidden realm of virtual messengers reveals something profound about forces themselves. What we experience as the fundamental forces of nature are actually continuous conversations between quantum fields, mediated by brief exchanges of virtual particles. The electromagnetic force speaks through virtual photons, the strong nuclear force through virtual gluons, the weak force through virtual W and Z bosons. Even gravity, though not yet fully understood quantum mechanically, likely involves hypothetical virtual gravitons carrying messages through the fabric of space-time itself. So here we float in this ocean of fields, where particles rise and fall like gentle ripples, where forces flow through invisible messengers, and where the vacuum itself hums with quiet, borrowed energy. But this picture leads to one of physics' most puzzling mysteries. If virtual particles constantly appear and disappear throughout space, then the vacuum should carry enormous amounts of energy. When physicists calculate this vacuum energy, they arrive at numbers so vast that if they were real, the universe would have expanded so rapidly after the Big Bang that stars and galaxies could never have formed. Yet here we are, in a cosmos that expanded at precisely the rate needed for complexity to emerge. This discrepancy between prediction and reality represents one of the deepest unsolved problems in science, reminding us that even our most successful theories still whisper mysteries beyond current understanding. As you rest there, consider that you're floating not in empty space but in an ocean of invisible activity. Every point around you teems with quantum fields in constant, gentle motion. The atoms of your body aren't isolated islands of matter, but temporary gatherings of field excitations, patterns of energy maintaining their form through continuous exchange with the quantum sea surrounding and permeating them. You are not separate from this ocean. You are a complex, beautiful wave pattern within it, a temporary organization of field fluctuations that has learned to observe itself, to wonder about its own nature. This understanding of reality as fields rather than objects, as processes rather than things, prepares us perfectly for our next gentle exploration. For if particles are ripples in quantum fields, and if these fields extend everywhere, then what happens when these ripples encounter barriers they seemingly cannot cross? Let your awareness soften as we prepare to witness how the quantum ocean sometimes finds ways to flow around the word impossible, allowing its gentle waves to appear on far shores without ever breaking through the obstacles between. Let that image of reality as an ocean of invisible fields rest gently in your awareness as we explore what happens when the gentle ripples we call particles encounter what should be insurmountable barriers. We've discovered that particles are temporary gatherings in vast, underlying seas of energy, waves rising and falling across infinite quantum fields. But what occurs when these field disturbances approach obstacles that classical physics insists they simply cannot overcome? Picture yourself standing before a towering stone wall, ancient and solid, stretching higher than you can see and wider than you can walk around. You press your hand against its cool, rough surface, feeling its absolute resistance. In our everyday world, you know with certainty that you cannot pass through this barrier. Your body, composed of countless atoms following classical rules, simply cannot occupy the same space as the wall's matter. This is the logic we live by, the world of definite boundaries and solid objects. But now imagine shrinking down to the scale of our familiar electron, that tiny ripple in the quantum field ocean. Picture this particle approaching a similar barrier, not made of stone but of energy, an invisible hill rising higher than the particle's own energy should allow it to climb. According to classical physics, the particle should simply bounce back, forever confined to its side of the energy wall. No way through, no exceptions, yet the quantum world, with its gentle, mysterious smile, whispers something extraordinary. Actually, there is a way. This is quantum tunneling, one of nature's most elegant acts of quiet rebellion against the word impossible. It's not magic, not cheating, not violation of fundamental laws. It's simply how the universe works at its most subtle, most profound level. When a quantum particle approaches an energy barrier, something beautiful happens. The wave function that describes the particle's existence doesn't stop abruptly at the barrier's edge like water hitting a dam. Instead, it behaves more like morning mist seeping through a fence, extending into the forbidden region where the particle supposedly has no right to exist. The wave grows weaker as it penetrates the barrier, like a melody heard faintly through a closed door, but it doesn't vanish completely. On the far side of the barrier, something remarkable occurs. The wave function continues, diminished but present, creating a small yet real probability that the particle might be found beyond the obstacle it could never classically surmount.
This isn't teleportation.
The particle doesn't disappear on one side and magically reappear on the other. Instead, its wave of possibility stretches continuously through the barrier, and occasionally that possibility crystallizes into reality on the far shore. This gentle art of slipping through walls is written across the cosmos in letters of light. Deep in our sun's core, hydrogen nuclei approach each other under immense pressure and temperature. Yet even these extreme conditions aren't quite enough to overcome the electrical repulsion between positively charged protons. Classical physics would predict that fusion should be impossible under solar conditions, that our star should be a cold, lifeless sphere drifting through space. But quantum tunneling provides the solution. The proton's wave functions extend beyond their classical boundaries, occasionally overlapping enough to allow fusion to occur, despite the energy barrier between them. Each successful tunneling event releases energy that eventually reaches us as sunlight, warmth, and the foundation for all life on
Earth. Every ray of sunshine that has ever touched.
Your face exists because particles found a way to slip through barriers they had no classical right to cross. But the probability of successful tunneling follows precise mathematical rules, like a cosmic equation balancing possibility against obstacle. A thin barrier offers better odds than a thick one. A low barrier presents less resistance than a towering wall. The particle's energy also matters, though even very low-energy particles retain some chance of breaking through. Most importantly, these probabilities decrease exponentially with barrier size, meaning that doubling the thickness doesn't merely halve the chance, but can crush it to near nothing. This is why you don't tunnel through your bedroom wall, no matter how many times you walk toward it. For objects made of countless particles, the probabilities collapse into effective impossibility across any reasonable time frame. You would need to wait longer than the age of the universe for even the slightest chance of success. The quantum world keeps its miracles abundant at the small scale, while preserving the reliable solidity we depend on in daily life. Tunneling also governs the patient process of radioactive decay. Within certain unstable atomic nuclei, alpha particles find themselves trapped in potential wells, held by nuclear forces yet repelled by electric charges. They should remain imprisoned forever, lacking sufficient energy to escape. Yet they do escape, tunneling through the energy barrier that surrounds them. We cannot predict when any individual nucleus will decay, but across large populations, this process occurs with statistical regularity, giving us the half-lives we use to date ancient artifacts and understand matter's structure. Modern technology depends intimately on quantum tunneling. The scanning tunneling microscope, which allows us to image individual atoms, works by measuring the tiny current that flows when electrons tunnel between a sharp metal tip and the surface being studied. Electronic devices throughout your home contain tunnel diodes designed to exploit this phenomenon, creating components with unusual properties that enable everything from high-frequency communications to precision circuits. As you rest there, surrounded by walls that remain reassuringly solid, consider the quantum drama unfolding within your very atoms. Electrons tunnel between energy levels, enabling the chemical reactions that sustain life. The boundary between possible and impossible, so clear in everyday experience, dissolves into gentle probability at the scale where existence's most fundamental processes unfold. There's something profoundly hopeful in tunneling's quiet persistence. It reminds us that barriers aren't verdicts, but filters, that the universe allows what seems forbidden, not recklessly, but with whispered grace. Perhaps that's why tunneling feels like wisdom as well as physics. When confronted with obstacles, sometimes the way forward isn't over or around, but through without force, with patient possibility. This understanding of how quantum waves slip through impossible barriers prepares us beautifully for our next gentle exploration. For if particles can tunnel through obstacles and exist in superposition simultaneously, what happens when we weave these phenomena into machines that think in maybe? Let your breathing slow as we prepare to enter a realm where quantum rebellion becomes quantum computation, where uncertainty transforms into a new kind of certainty, and where these strange possibilities we've discovered become tools for exploring
Reality's deepest questions and let you.
that image of particles gently slipping through impossible barriers. Rest in your awareness as we follow this thread of quantum rebellion into something even more extraordinary. We've witnessed how the universe allows what seems forbidden, how wave functions extend beyond classical boundaries with patient persistence. But what happens when we harness these quiet acts of rebellion against impossibility? What emerges when we weave superposition, tunneling, and entanglement into machines designed to think in the universe's native language of maybe? Picture the computer humming quietly nearby, the one playing this very narration. Deep within its circuits, information flows as bits, each one a simple binary choice like a light switch. 0 or 1, off or on, yes or no. Every calculation, every word, every gentle sound reaching your ears emerges from vast cascades of these definite digital decisions. It's remarkably elegant in its certainty, like a cosmic conversation conducted entirely in nods and shakes of the head.
Millions of tiny verdicts rendered each second with breathtaking precision. But imagine a different kind of machine.
One that speaks the native language of the quantum realm we've been exploring together. Instead of bits locked into 0 or 1, this device uses quantum bits, qubits, that embrace the superposition we met in our spinning coin. These qubits can be both 0 and 1 simultaneously, holding multiple possibilities in gentle suspension until measurement asks them to choose, just like that electron existing in multiple locations until someone looks. This isn't merely a faster way of processing the same information. It's an entirely different relationship with knowledge itself. Where a classical bit must commit to a single state, a qubit in superposition explores multiple states at once, like our electron flowing through both slits simultaneously. 2 classical bits can represent 4 possible combinations, but only one at a time, marching through them sequentially. 2 qubits in superposition can represent all 4 combinations simultaneously, existing in that beautiful quantum space where everything remains possible until something asks for an answer. As we add more qubits, this multiplicative magic compounds exponentially, like ripples spreading across our quantum field ocean. 3 qubits can represent 8 states at once, 4 qubits, 16 states, and so on. By the time we reach just 20 qubits, we're dealing with over 1 million simultaneous states held in quantum suspension. 50 qubits could represent more possibilities than there are atoms in your body, all available for computation in the same gentle moment. But here's where the story becomes both more complex and more beautiful. These qubits don't just exist independently in their individual superpositions. They can become entangled, those invisible threads we glimpsed earlier, weaving them into a single, unified quantum system. When qubits entangle, measuring one instantly influences the others, creating correlations that span the entire quantum processor. The machine becomes not just a collection of maybe bits, but a single, coherent quantum entity exploring vast landscapes of possibility in parallel. This parallel exploration gives quantum computers their extraordinary potential. Instead of checking each possible solution one at a time like a classical computer, methodically trying every key on an enormous ring, a quantum computer can test many solutions simultaneously. It's like having a master key that opens multiple locks at once, or like that magical librarian who reads every book in the library simultaneously to find the single piece of information you need. Consider Shor's algorithm, which demonstrates that quantum computers could factor large numbers exponentially faster than any classical approach. This matters deeply for cryptography, since much of our digital security relies on the difficulty of factoring enormous numbers. Then there's Grover's algorithm, which speeds up searches through unstructured databases, not miraculously, but meaningfully. Perhaps most exciting is quantum simulation itself, using quantum machines to model other quantum systems, letting molecules describe molecules, chemistry describe chemistry, with unprecedented precision. Yet this quantum advantage comes with its own gentle challenges. The superposition states that make quantum computation possible are extraordinarily fragile, like soap bubbles that burst at the slightest disturbance. Heat, vibration, stray electromagnetic fields, even cosmic rays can collapse a qubit's delicate superposition, destroying the quantum information it carries. This is decoherence, the same phenomenon that keeps cats from existing in superposition, now becoming the primary engineering challenge for quantum computers. To preserve these delicate quantum states, qubits must be cradled in extreme stillness. Some researchers use individual atoms trapped by precise electromagnetic fields, their quantum states encoded in electron spin. Others employ superconducting circuits, tiny loops of metal cooled until electrons flow without resistance, creating quantum states from collective particle behavior. Still others explore photons of light, encoding information in their polarization, creating quantum processors from carefully controlled beams of luminescence. Each approach brings its own poetry of precision. Trapped atom systems offer exquisite control but require complex laser orchestration. Superconducting circuits can leverage familiar manufacturing techniques but demand temperatures colder than deep space. Photonic systems operate at comfortable temperatures but face challenges in creating the strong qubit interactions that complex calculations require. Even with these challenges, quantum computers are beginning to demonstrate capabilities that would take classical computers longer than the age of the universe to complete. This isn't just about speed, it's about accessing entirely new categories of solvable problems, like discovering new continents in the ocean of computation. They excel at optimization problems, finding the best solution among countless possibilities. They show promise for drug discovery, materials science, and understanding chemical reactions with quantum-level accuracy. Perhaps most remarkably, quantum error correction is emerging as a second art, weaving many physical qubits into single logical qubits the way you might braid fragile threads into strong rope. The braid is designed so tiny, frays can be detected and smoothed before the whole strand snaps, building resilience from cooperation, order from redundancy. As you lie there, perhaps feeling your own consciousness hovering between the definite state of wakefulness and the superposition of dreams, consider that quantum computing represents humanity's first attempt to build machines that think like the universe itself thinks at its deepest level. Instead of forcing reality into binary logic, these devices embrace uncertainty, superposition, and entanglement as computational resources. There's something profoundly moving about this technological poetry. We're creating machines that don't just calculate answers, but explore spaces of possibilities, devices that hold multiple realities in suspension till measurement crystallizes one path forward. In a sense, quantum computers are teaching us to think more like the quantum fields we emerged from, to work with uncertainty rather than against it, to find power in maybe rather than demanding false certainty. This embrace of quantum thinking, this willingness to build machines that speak the universe's native language of probability and possibility, prepares us perfectly for our next gentle exploration. For if we can create devices that think in superposition, if we can harness uncertainty as a resource, then perhaps we're ready to address the deepest question quantum mechanics poses. What does it all mean? Let your awareness soften as we prepare to explore the various ways brilliant minds have tried to interpret this quantum mystery, the different stories we tell about what reality actually is when no one is looking, and how these interpretations shape our understanding of existence itself. Let that understanding of machines thinking in the universe's native language of possibility rests gently in your awareness as we approach the deepest question our quantum journey
has been quietly building toward.
We've discovered particles that dance in superposition, wave functions that collapse upon observation, and computers that harness uncertainty as a resource. The mathematics works with breathtaking precision, predicting outcomes with accuracy that would make the most careful clockmaker weep with wonder. Yet beneath all this mathematical elegance lies a profound mystery that has captivated minds for nearly a century. What does it all actually mean? This brings us to the interpretations of quantum mechanics, different ways of listening to the story reality tells when we're not looking. Think of quantum theory as a beautiful, intricate poem written in the language of mathematics. We can recite it perfectly, its rhythm and structure are undeniably elegant, and it makes predictions that match the world with stunning precision. But when asked what the poem actually says about the nature of existence itself, we find ourselves offering different possible meanings, each one plausible, each one resonating with different aspects of human understanding. These interpretations don't change the mathematics or alter the predictions. They're more like different lenses through which we view the same mysterious landscape, compass roses rather than destinations, helping us point our curiosity in various directions without claiming final ownership of the horizon. Each interpretation offers its own gentle wisdom about what reality might be doing in those quiet moments between questions and
Answers. Let's begin our soft stroll through these.
possibilities with the Copenhagen interpretation, developed by Niels Bohr and his colleagues in the 1920s. This view offers a kind of philosophical minimalism, practical and modest in its claims. Copenhagen suggests that the wave function is primarily a tool for calculating probabilities, not necessarily a direct portrait of objective reality. In this gentle pragmatism, quantum systems don't possess definite properties until they're measured. That electron we've been following doesn't secretly harbor a specific location while existing in superposition. It genuinely occupies a spread of possibilities and only measurement asks it to choose, causing the wave function to collapse into a single, definite outcome. Copenhagen emphasizes something called complementarity, the recognition that particles can behave like waves or like particles, but the context of measurement determines which face they show us. It's a bit like saying, don't ask what's really happening behind the curtain. The theory works beautifully, and that's enough wisdom for now. For many physicists, this practical approach has been deeply satisfying, allowing them to build technologies and make predictions without getting tangled in philosophical mysteries. But some minds have never been content to stop asking what lies beneath the surface. This brings us to the many worlds interpretation, proposed by Hugh Everett III in the 1950s. This remarkable vision removes one of Copenhagen's most puzzling features by suggesting that the wave function never collapses at all. Instead, every possible outcome of a quantum measurement actually occurs, but in separate branching realities that continuously split from each other like tributaries flowing from a great river. When you measure that electron spin and observe it pointing up, somewhere else in the vast tree of parallel universes, another version of you observes it pointing down. The universe doesn't choose one outcome. It embraces all outcomes, each in its own branch of reality. This branching happens not just for electrons, but for every quantum event, constantly and endlessly, creating an incomprehensibly vast multiverse where every possibility finds expression. In this view, superposition isn't temporary indecision, but a real physical state that evolves deterministically, with the randomness we observe simply reflecting our residence in one particular branch of the cosmic tree. Now let's drift towards something more classically comfortable. Pilot wave theory, also known as Bohmian mechanics. This interpretation suggests that particles always have definite positions and velocities, like familiar objects in our everyday world. They're not probability clouds, but real physical things moving along specific paths. But they don't travel alone. They're guided by an invisible pilot wave, the wave function itself, which steers their motion like a hidden current directing a boat through water. This theory is entirely deterministic. If you knew all the initial conditions perfectly, you could predict everything that would happen. The strange quantum effects like interference and tunneling emerge naturally from this guiding wave, even though the particle follows only one definite path. It restores a kind of classical realism to physics, though it requires accepting that this pilot wave can coordinate particles instantly across vast distances, creating connections that span space without crossing it. For those who prefer reality to make its own decisions without requiring observers, there are objective collapse theories. These suggest that wave functions spontaneously collapse over time, especially when quantum systems become large or complex enough. The universe itself decides when possibilities crystallize into facts, without needing measurement or observation to trigger the transition. One well-known version introduces occasional random collapses into the wave function's evolution, more frequent for larger systems, elegantly explaining why we never see cats or tables in superposition while preserving quantum behavior at microscopic scales. Then there's cubism, short for quantum Bayesianism, which takes a deeply personal approach to the mystery. In this view, the wave function isn't a description of objective physical reality, but a reflection of an observer's knowledge and beliefs about a quantum system. Quantum probabilities don't exist out there in the world. They live inside us as agents making careful predictions about future experiences. When measurement happens, it doesn't collapse an objective wave function, but updates our subjective beliefs, like a thoughtful gambler revising strategy after seeing new information. Cubism shifts focus from objective reality toward subjective experience.
From what the world is toward how we interact with it.
It's philosophically sophisticated and mathematically rigorous, but it sidesteps questions about what the wave function represents in favor of focusing on how we use it to navigate our encounters with the quantum world. As you rest there, perhaps feeling your own consciousness existing in a kind of superposition between wakefulness and the approaching realm of dreams, consider that none of these interpretations has been definitively proven. Each remains consistent with known experiments while offering different stories about reality's deepest nature. Some physicists choose favorites, others work without interpretation, and still others embrace the uncertainty itself as a feature rather than a flaw. Perhaps like quantum systems themselves, our understanding can exist in superposition, embracing multiple possibilities without needing to collapse into a single belief. These interpretations function like different lullabies for the mind, soothing various kinds of curiosity. If you long for practical clarity, Copenhagen offers gentle boundaries around what can be known. If you crave completeness, Many Worlds provides a vast, continuous sky where nothing is lost. If you prefer definite paths, pilot waves promise hidden guidance beneath apparent randomness. If you want collapse without observers, objective theories let the universe make its own decisions. If you prefer mathematics as a personal tool, subjective approaches let the wave function rest gently in your hands rather than demanding you stand upon an objective stage. This philosophical richness, this abundance of possible stories about quantum reality, reminds us that precision and humility can coexist beautifully. The wave function solves and suggests answers and invites, predicts and preserves mystery, and perhaps that's not a limitation but a gift, an invitation to remain comfortable in the space between questions and answers, to let wonder flourish alongside understanding. This openness to multiple truths, this willingness to hold various interpretations in gentle suspension, prepares us perfectly for our next quiet exploration. For while physicists debate the meaning of quantum mechanics in academic halls, quantum phenomena may be quietly shaping the living world around us in ways both subtle and profound. Let your breathing deepen as we prepare to discover whether the quantum realm we've been exploring together might be woven into the very fabric of life itself. From the leaves that capture sunlight with mysterious efficiency to the birds that navigate by invisible quantum compasses, perhaps even to the delicate processes that might underlie the miracle of consciousness itself. Let that openness to multiple truths, that willingness to hold various interpretations in gentle suspension, carry us from the halls of theoretical physics into something far more intimate and immediate. While brilliant minds debate what quantum mechanics means in academic quiet, something extraordinary may be happening all around us, woven into the very fabric of the living world that cradles you each night. The quantum mysteries we've been exploring together might not be confined to sterile laboratories or abstract equations, but quietly humming in every leaf, every breath, every heartbeat. For much of modern science, biology and quantum mechanics seemed like distant neighbors,
rarely speaking across the fence between them.
Biology thrived in the warm, wet, noisy complexity of cells and tissues, while quantum physics preferred the cold isolation of subatomic particles. One dealt in blood and chlorophyll, the other in wave functions and probability clouds. Yet, over the past few decades, a new field has begun to blossom in the space where these worlds meet: quantum biology, offering us glimpses of a universe far more interconnected than we ever imagined. Begin with something green and essential, perhaps a leaf outside your window catching the last light of evening. Photosynthesis seems straightforward enough. Sunlight strikes the leaf, energy transfers through molecular machinery, and carbon dioxide transforms into the sugar that feeds nearly all life on Earth. But when researchers examined this process with quantum precision, they discovered something that shouldn't be possible according to classical expectations. When a photon from the sun touches a leaf, it creates an exciton, a packet of energy that must travel from the antenna pigments where it's captured to the reaction center where chemistry happens. In classical physics, this energy would wander randomly through a molecular maze, bouncing around like a pinball until it eventually, hopefully, reaches its destination. But nature, it seems, has found a more elegant solution. Evidence suggests that during this energy transfer, the exciton doesn't choose a single path through the photosynthetic machinery. Instead, it explores multiple routes simultaneously, existing in quantum superposition as it flows through the leaf's molecular architecture. Like our electron passing through both slits at once, the energy packet samples all possible pathways and then, through quantum interference, finds the most efficient route to its destination. The leaf becomes a soft tutor, teaching us that evolution discovered quantum engineering long before we gave it a name, achieving nearly perfect energy transfer efficiency through coherence that somehow survives in warm, living tissue. Now let your awareness drift skyward with the migrating birds that trace invisible highways across continents. European robins, Arctic terns, and countless other species perform these journeys with breathtaking precision, guided by something we're only beginning to understand. Some researchers believe these birds possess quantum compasses in their very eyes, biological systems that literally see magnetic fields through quantum entanglement. The theory centers on molecules called cryptochromes found in bird retinas. When light strikes these molecules, it creates pairs of electrons with entangled spins, those invisible quantum threads we explored earlier. Earth's magnetic field, weak as it is, can influence how these entangled electrons evolve, shifting the balance between different quantum states. This shift changes the chemical outcome of the reaction, potentially creating visual patterns that guide the bird like constellations etched upon daylight.
Vision. Imagine seeing not just the
landscape below, but also the invisible magnetic highways that crisscross the planet. Quantum entanglement in your eyes, translating Earth's gentle magnetic whispers into navigational guidance. Laboratory studies have shown that disrupting these quantum states with certain wavelengths of light can indeed interfere with a bird's ability to navigate, as if someone had smudged the compass in its eye, even closer to your resting form. Quantum effects may shape the very sense of smell that might be detecting evening air drifting through your window. The traditional theory suggests smell works like lock and key, molecules fitting into receptors based on shape alone. But this struggles to explain why some molecules with nearly identical shapes smell completely different. while others with very different structures smell exactly the same. This puzzle led researchers to propose that smell might involve quantum tunneling, that gentle art of slipping through barriers we discovered earlier. In this vibrational theory of olfaction, when a scent molecule binds to a receptor, it vibrates at a specific frequency. If that vibration matches the receptor's quantum requirements, it enables electrons to tunnel through energy barriers within the receptor protein. Only when the molecular vibration strikes the right quantum note does the electron make its tunneling leap, triggering the neural signal that becomes the scent of roses or vanilla or fresh rain. Perhaps most intriguingly, some researchers have wondered whether quantum effects might touch consciousness itself. The warm, wet environment of the brain seems hostile to quantum coherence, yet theories suggest that microscopic structures called microtubules within neurons might provide protected spaces where quantum processes could survive long enough to influence thought. This remains highly speculative, but it raises the tantalizing possibility that your thoughts drifting towards sleep might be supported by quantum processes reaching down to reality's deepest levels, whether or not consciousness involves quantum mechanics. This emerging field reveals something profound about evolution's relationship with the quantum world. Natural selection, operating over millions of years with countless tiny experiments, may have discovered ways to harness quantum effects that human technology is only beginning to explore. Life, it seems, might be quantum engineering at its most sophisticated, using superposition, entanglement, and tunneling, not as curiosities, but as practical tools for survival. Your body becomes an orchestra tuned by physics, each instrument small and precise, humming with quantum rules that evolution has refined across deep time. The mystery isn't that quantum phenomena appear in messy,
living places, but that life has coaxed reliability from the unreliable.
Taming probability into function the way a musician tames vibration into song. As you rest there, consider that every breath might involve quantum processes. Every heartbeat might depend on tunneling effects. Every moment of awareness might emerge from systems subtly tuned to work with rather than against quantum nature. You are not separate from the quantum world we've been exploring. You are made of it, shaped by it,
Perhaps even consciously experiencing it in ways we're only
beginning to understand. This recognition that quantum effects may be intimately
woven into life itself prepares us.
perfectly for our next gentle exploration. For if quantum mechanics governs biological processes and shapes the smallest scales of existence, then it must also underlie the grand structures of the cosmos itself. Let your awareness expand as we prepare to discover how these quantum rules scale up from atoms to stars to galaxies, revealing a universe where the strange and familiar emerge from the same underlying symphony, playing at every scale from the infinitesimal to the infinite. Let that recognition of quantum effects, woven intimately into the fabric of life itself, expand gently outward, like ripples spreading across a still pond at dawn. We've discovered how evolution may have learned to harness superposition in leaves catching sunlight, entanglement in birds navigating by invisible magnetic highways, and tunneling in the delicate chemistry of scent and sensation. But if quantum mechanics can shape the most intimate processes within living cells, then it must also underlie the grand architecture of existence itself, scaling from the infinitesimal to the infinite in ways that connect your quiet breathing to the light of distant stars. Begin with something wonderfully close to home: the atoms that compose your resting body. We often picture electrons orbiting atomic nuclei like tiny planets circling a miniature sun, but this classical image, while comforting in its familiarity, is far too rigid for quantum truth. Instead, electrons exist in orbitals, not fixed paths but probability clouds, regions of space where they're most likely to be found but never confined to definite trajectories. These orbitals have precise shapes and energies determined by solutions to quantum wave equations that read like mathematical poetry describing the architecture of matter itself. Think of these energy levels as rungs on an invisible cosmic ladder. An electron cannot hover between steps. It must occupy one specific quantum state, and only certain energies are permitted. This quantization gives each atom its unique personality, its chemical signature written in the language of allowed and forbidden transitions. When an electron drops from a higher energy level to a lower one, it releases a photon with a color that perfectly matches the energy gap between those quantum rungs. The warm glow of gold, the reddish shine of copper, the brilliant spectrum of hydrogen in distant stars, all emerge from this quantum choreography of electronic transitions. But there's something even more fundamental at work here, a quantum rule that literally prevents the universe from collapsing into formless chaos. The Pauli exclusion principle, discovered by Wolfgang Pauli, operates like an invisible cosmic guest list, ensuring that no two electrons can occupy exactly the same quantum state simultaneously. Imagine trying to seat dinner guests where no two people are allowed in identical chairs, even if the chairs are perfectly similar. Electrons, being fastidious quantum guests, must spread out into different energy levels, different orbital shapes, building up layers around atomic nuclei like the delicate shells of an invisible onion. This quantum social distancing is what gives matter its size and solidity. Without the exclusion principle, all electrons would crowd into the lowest energy state, atoms would shrink to points, and the resistance you feel when your hand presses against the surface beside you would simply vanish. That gentle firmness, that reassuring boundary between your body and the world, emerges from countless electrons politely refusing to share quantum states. You don't sink through your bed because electrons maintain their quantum boundaries with mathematical precision. When atoms approach each other to form molecules, quantum mechanics orchestrates every connection with exquisite care. Chemical bonds aren't tiny hooks or cosmic glue, but quantum phenomena, where electrons create molecular orbitals, probability clouds that span multiple atoms simultaneously. These shared electron states determine molecular shapes, bond angles, and chemical properties with breathtaking precision. The bent geometry of water molecules, the carbon chains that form the backbone of organic compounds, the complex folding patterns of proteins that enable life itself, all emerge from quantum rules governing how electron waves combine and interfere across atomic boundaries. Every enzyme reaction sustaining your metabolism, every strand of DNA preserving your genetic information, every neurotransmitter carrying signals through your nervous system represents quantum mechanics operating at biological scales. Your body is an intricate quantum chemistry laboratory, maintaining the delicate conditions necessary for wave functions to collapse into the precise molecular arrangements that enable consciousness, breath, and the gentle drift towards sleep. Now let your awareness expand beyond Earth's protective atmosphere to the stars themselves, those distant points of light that have guided travelers and dreamers across countless centuries. Deep in stellar cores, temperatures and pressures reach extremes that would vaporize any earthly material. Yet even these conditions aren't quite sufficient to overcome the electrical repulsion between atomic nuclei. Hydrogen nuclei, being positively charged, should bounce off each other like magnets of the same polarity pushed together, their mutual repulsion growing stronger as they approach. Yet fusion occurs throughout the cosmos, powering every star in the night sky through quantum tunneling, that gentle art of slipping through impossible barriers we discovered earlier. Protons approach each other, and occasionally their wave functions overlap enough to allow fusion despite the classical energy deficit. Each successful tunneling event releases energy that eventually reaches us as starlight, warmth, and the foundation for the complex chemistry that makes planets and life possible. Without quantum tunneling, stars would never ignite, the universe would remain cold and dark, and the heavy elements necessary for complexity would never form in stellar furnaces. Every photon that has ever warmed your face, every carbon atom in your body, every oxygen molecule you breathe exists because quantum mechanics allows the seemingly impossible in the hearts of stars scattered across space and time. The sun's gentle energy reaching through your window carries the signature of countless quantum tunneling events occurring at rates that stagger the imagination, each one a tiny victory of possibility over classical prohibition. When massive stars exhaust their nuclear fuel and begin their final collapse, quantum effects determine their ultimate fate with cosmic drama. Some become white dwarfs, stellar corpses held up not by the heat of fusion, but by electron degeneracy pressure, the same Pauli exclusion principle that gives atoms their size, now operating on stellar scales. The electrons refuse to be compressed beyond quantum limits, creating outward pressure that prevents further gravitational collapse. A white dwarf is essentially a city-sized atomic nucleus held stable by quantum mechanical rebellion against compression. Even more massive stars collapse further into neutron stars, where gravity overcomes electron degeneracy and forces protons and electrons to combine into neutrons. These incredibly dense objects, where a teaspoon of material would weigh as much as a mountain, are held up by neutron degeneracy pressure, quantum mechanics operating at the very edge of what matter can withstand. In the most extreme cases, even quantum pressure cannot resist gravity's pull, and black holes form regions where space-time itself curves so severely that not even light can escape, marking the boundaries. Where our current understanding of quantum mechanics meets its greatest mystery, the early universe itself was a quantum playground where the largest and smallest scales dance together in cosmic choreography. Many cosmologists believe that quantum fluctuations in the primordial vacuum, tiny random variations in energy density smaller than atomic nuclei, were stretched by cosmic inflation into the large-scale structure we observe today. The galaxies scattered across the night sky, the vast cosmic web of matter spanning billions of light-years, even the mottled pattern of the cosmic microwave background radiation, all trace their ancestry to quantum uncertainty magnified to astronomical proportions by the universe's expansion. In this extraordinary picture, every star you might glimpse through your window, every planet orbiting distant suns, every cosmic structure visible to our most powerful telescopes, emerge from quantum fluctuations that once existed in spaces smaller than the nucleus of an atom. The universe we inhabit is quantum mechanics written large, uncertainty and probability sculpted by expansion and gravity into the cosmic architecture that cradles our existence. As you rest there, woven into this vast quantum tapestry, consider that the atoms in your body were forged in stellar furnaces through quantum processes, dispersed by stellar explosions and gathered by gravity into the planet that supports your life. You are made of star stuff, but more precisely, you are made of quantum star stuff.
Matter, whose every property emerges from the same wave functions and
Probability clouds we've been exploring together throughout this gentle journey, the boundary between the quantum and classical. Worlds isn't a sharp wall, but a soft gradient, a gentle transition where quantum strangeness gradually gives way to familiar solidity through the accumulation of countless tiny effects. The robust stability of everyday objects emerges from the collective behavior of quantum particles, their individual uncertainties smoothed into statistical certainties through the magic of large numbers. Yet the quantum foundation never disappears completely. It simply hides beneath the surface, supporting the apparently solid world with an invisible architecture of probability and possibility, connection and gentle mystery. This understanding of quantum mechanics as the hidden foundation of everything, from atoms to stars to the cosmic web itself, brings us naturally to a moment of quiet reflection. For while quantum physics reveals profound truths about reality's deepest nature, it has also gathered around itself a collection of myths and misunderstandings that deserve gentle clarification. Let your breathing slow and deepen as we prepare to clear away some common misconceptions with kindness and curiosity. ensuring that the wonder we've discovered together rests on solid ground rather than wishful thinking, distinguishing between the genuine magic of quantum mechanics and the attractive but inaccurate stories that sometimes gather around its mysterious edges. Let that understanding of quantum mechanics as the hidden foundation of everything, from the atoms composing your resting body to the light of distant stars, settle gently around you like a soft blanket on a cool evening. We've journeyed through landscapes of authentic wonder, discovering particles that dance in superposition, wave functions that collapse upon observation, and the delicate quantum processes that may underlie life itself. Yet for all its genuine mystery and mathematical beauty, quantum physics has also gathered around itself a collection of attractive misconceptions, like morning mist that can obscure the true landscape beneath. Perhaps it's because quantum mechanics is so beautifully counterintuitive, so far removed from everyday experience that it becomes a magnet for wishful thinking. Or perhaps it's because the mathematics describing quantum behavior is so precise and successful that people assume it must validate every strange idea that wanders into its vicinity. Whatever the reason, let us now take a gentle lantern in hand and walk softly through some of these mists, clearing away the fog with kindness and curiosity, not to scold but to soothe, replacing anxious mystery with grounded awe. One of the most persistent quantum myths whispers that your thoughts can directly reshape physical reality, that consciousness controls the quantum world through some mystical connection. It's an understandable leap, deeply appealing to our human desire for agency and meaning. If observation collapses wave functions, then surely focused intention must be a cosmic remote control, arranging electrons and bending reality to will. Yet when physicists speak of observation, they mean something quite specific: measurable interaction between a quantum system and its environment, not conscious awareness or focused thought. A photon detector clicking is an observation. A stray air molecule bumping into an electron is an observation. The world doesn't pause, waiting for human consciousness to arrive before proceeding with its quantum business. Instead, it decoheres continuously through countless interactions occurring every moment throughout space and time. Your thoughts matter profoundly in shaping your choices, your relationships, your understanding of the world, but they don't rearrange particles through quantum telepathy or bend spoons through meditation. The truth is quieter and more beautiful. Reality responds not to wishes, but to relationships, to contact, to the ways systems meet and exchange information. Another shimmering myth suggests that quantum entanglement provides a cosmic telegraph, allowing instant communication across any distance. The heart of this misconception lies in entanglement's genuine strangeness. Two particles, once connected, do share correlations that reveal themselves instantly when measured, regardless of separation. But those outcomes are fundamentally random, like opening sealed envelopes that always contain perfectly matched but unpredictable numbers. You cannot choose what result you'll observe, so you cannot encode messages at random. Only when you compare notes later through ordinary communication, still limited by light's patient speed, do the matched patterns appear. Entanglement creates profound connection, but it carries no signals. The cosmic speed limit remains as calm and unwavering as a distant horizon. Then there's our famous feline friend. Schrödinger's cat, often misunderstood as proof that cats can literally exist in superposition, simultaneously alive and dead until someone peeks into the box. This interpretation misses the point entirely and leads to the absurd conclusion that reality depends on human observation in ways that would make everyday life impossible. Schrödinger never meant for his cat to be taken literally. He was pointing out how odd quantum rules would seem if applied wholesale to large, warm, noisy objects constantly bathed in environmental interactions. A real cat breathes air,
Radiates heat, vibrates with every heartbeat.
existing in continuous measurement by countless environmental factors that collapse any potential superposition nearly instantaneously. The thought experiment serves as a bridge between the quantum realm, where superposition flourishes, and our classical world, where it becomes vanishingly rare, helping us understand why quantum strangeness remains hidden in everyday experience while governing the microscopic realm with mathematical precision. Sometimes the fog thickens into the broader claim that quantum physics means everything is random, chaotic, unmoored from order. Yet the equations of quantum theory yield predictions so precise we've built lasers, medical imaging devices, GPS satellites, and the very processors humming quietly nearby. Individual quantum events can be probabilistic, yes, but those probabilities are exquisitely structured, like a sophisticated weather forecast that cannot promise where each raindrop will land, but can predict the storm's behavior with remarkable accuracy. Across many trials, patterns emerge with astonishing reliability. The universe doesn't throw dice wildly, it rolls them with mathematical precision. From there, it's a short step to imagining that quantum mechanics makes anything possible, that rules melt into wishful thinking, that all boundaries become illusions. But the quantum world is not a dream without grammar. It operates according to strict mathematical syntax where energy is conserved, causality maintains its careful rhythms, and even tunneling obeys probabilities that shrink dramatically with barrier thickness. The universe offers latitude, not license. The strange is permitted, but it's also measured, weighted, and woven into inviolable law. There's another tender confusion that quantum language somehow grants instant healing or effortless transcendence through vague quantum influence. The desire behind this is beautifully human, honest longing for relief and wholeness, but trust rests more safely in what we can verify. Medicine grounded in evidence, care rooted in compassion, habits gently practiced over time. These are the reliable bridges to well-being. Quantum mechanics is a careful description of how the small behaves, and its gifts arrive through painstaking work and tested understanding. Not magical thinking. Clearing these mists doesn't dim wonder, it brightens it. There is grace in a universe that respects limits, that hides delicacy under law. A cosmos where probabilities are honest, where uncertainty has boundaries, where entanglement connects without breaking causality, proves itself trustworthy. It lets us build, heal, and understand without demanding every answer immediately. Precision and mystery become companions rather than rivals. If you've ever embraced one of these myths, there's nothing to regret. They arise from longing to belong to the cosmos, to feel its pulse within your own. The truer connection is subtler but no less intimate. Every breath passes through quantum-shaped molecules. Every photon touching your skin has tunneled from a stellar heart. Every thought riding the gentle rhythm of your breathing depends on quantum rules that keep atoms spacious and chemistry alive. You're not separate from the strangeness. You are its expression in a warm, conscious form. Let the certainty that quantum physics is both wonderfully weird and mathematically reliable serve as a kind of lullaby. The equations work with breathtaking precision. The technologies function flawlessly. The stars burn steadily. The leaves capture light with efficiency. We're only beginning to match. Beneath the myths, the authentic story proves even more comforting. The universe isn't capricious but intricate, not fickle but faithful to patterns we can learn, refine, and share. As your awareness grows softer and your breathing deeper, we prepare to gather all the threads we've followed together into one final, gentle reflection. We'll weave superposition's poise, uncertainty's tenderness, entanglement's quiet bonds, and observation's conversation into a single resting thought, not an answer that closes doors, but a way of holding questions that keeps them tender and true. On your next breath, we'll step into that soft horizon where our story doesn't end so much as settle, like starlight coming to rest on still water, and everything improbable begins to feel like home. Let that certainty that quantum physics is both wonderfully weird and mathematically reliable settle around you like a gentle evening mist as we gather all the threads of our journey into one final, tender reflection. We've cleared away the fog of misconception, not to diminish wonder, but to let authentic mystery shine more clearly, like stars emerging as twilight deepens. Now, as your breathing grows softer and your awareness drifts into that peaceful space, between wakefulness and dreams, we can weave together everything we've discovered into a single, seamless understanding. Think back to where we began with that simple invitation to imagine particles that refuse to choose just one place to be, and a universe that seems to prefer maybe over yes or no. We've traveled through landscapes where electrons exist in superposition, dancing in multiple states simultaneously like a breath held between possibilities. We witnessed the elegant mystery of the double-slit experiment, watching single particles interfere with their own potential paths, painting patterns that whispered of a reality far more fluid than our senses perceive. We embraced the tender truth of uncertainty itself, learning that the universe maintains soft boundaries around simultaneous knowledge. The more precisely we pin down one aspect of reality, the more another dissolves into beautiful indeterminacy, not because of our limitations, but because uncertainty is woven into existence's deepest fabric. We discovered invisible threads called entanglement, where particles born together remain intimately connected across vast distances, sharing correlations that Einstein called spooky, but which simply express quantum truth in its purest form. We learned that observation is never passive but always participatory, that the simple act of looking transforms wave functions from clouds of possibility into definite outcomes. Reality doesn't just allow questions, it requires them to complete itself. You are not separate from the quantum conversation, but woven into it as both observer and participant, helping to collapse infinite potential into the singular beauty of each measured moment. Beneath all these phenomena, we dove into the vast ocean of quantum fields, discovering that particles aren't solid specks, but gentle ripples in an all-pervading sea of energy. Even empty space hums with virtual particles appearing and disappearing, mediating the forces that bind atoms and light stars. We watched particles tunnel through impossible barriers, enabling the fusion that powers our sun and makes life possible. Through quantum rebellion against classical prohibition, we glimpsed machines learning to think in the universe's native language of probability, quantum computers that harness superposition and entanglement to explore vast solution spaces simultaneously. We explored how evolution may have discovered quantum engineering millions of years before human science, using coherence in photosynthesis, entanglement in bird navigation, and tunneling in the chemistry of scent and sensation. From atoms to stars to the cosmic web itself, we traced how quantum rules scale up through every level of reality. The solid feeling of your resting surface, the warmth of your breath, the gentle rhythm of your heartbeat, all emerge from quantum processes operating with mathematical precision beneath ordinary perception. You are not observing quantum mechanics from outside. You are quantum mechanics temporarily organized into a pattern complex enough to observe itself. Throughout our journey, one truth has emerged with quiet consistency. The quantum world reveals reality as fundamentally relational rather than mechanical. Instead of isolated objects moving through empty space, we find interconnected patterns, dynamic processes, ongoing conversations between possibility and actuality. The universe emerges through relationship, through measurement, through the gentle touch of curiosity meeting mystery. This understanding transforms how we hold existence itself. Quantum mechanics invites us to expand our notion of what's possible while maintaining precise mathematical boundaries. Uncertainty has limits. Tunneling follows probabilities. Entanglement creates profound connection without enabling faster-than-light communication. The quantum realm isn't chaos, but structured mystery, not randomness but patterned possibility dancing within inviolable laws. Perhaps most beautifully, we've learned that precision and humility can dance together. We can make extraordinarily accurate predictions while remaining open about their deepest meaning. We can build technologies that work flawlessly while acknowledging that fundamental questions remain tenderly unresolved. The universe proves both reliable enough to support complex structures like consciousness and flexible enough to surprise us with new possibilities at every scale. As you rest there, perhaps noticing how your own awareness hovers between the definite state of wakefulness and the superposition of approaching dreams, consider that you're experiencing your own version of quantum complementarity. Focus and drift, certainty and wonder, question and acceptance can coexist without contradiction, each revealing different aspects of what it means to be conscious in a participatory universe. The myths we gently cleared away weren't entirely wrong in sensing profound connections between mind and reality, between observation and existence. They simply located those connections in wishful places rather than recognizing the subtler, more beautiful truth, genuine participation in reality's ongoing self-creation through every question we ask and every measurement we make. Standing here at journey's end, we can see that quantum mechanics offers more than descriptions of laboratory phenomena. It provides a new way of being in relationship with mystery itself, a practice of holding questions with patience, embracing uncertainty as creative potential, and recognizing that the boundaries between observer and observed are far softer than classical physics suggested. The endless dance of our title isn't metaphorical, but literal truth. Particles and fields, possibilities and actualities, questions and answers remain always in motion, always in relationship, always creating the next moment through their interactions. You are part of that dance, not watching from the sidelines, but as conscious quantum fields that have learned to wonder about their own nature. So as your thoughts begin their gentle drift towards sleep, let this be your final understanding. You live in a universe, stranger and more beautiful than everyday experience suggests, more connected and responsive than classical physics allowed, more open to possibility while remaining faithful to mathematical patterns. The quantum realm isn't distant abstraction, but the intimate foundation of every breath, every dream, every moment of wonder. Now let me ask one final time, where in the world are you listening tonight? What time is it in your cozy corner of the cosmos? If this gentle journey through quantum mystery has helped you wind down or filled your evening with wonder, please consider giving this video a like and subscribing to The Whispering Scientist for more calm adventures through science
and sleep.
In the end, uncertainty isn't something to be solved, but something to be danced with. Mystery isn't a problem, but a partner. Sleep well, knowing you're woven into the quantum fabric of existence itself, where every particle is a probability, every measurement a conversation, and every dream a gentle collapse of infinite possibility into the singular grace of this moment, breathing softly in a universe that never stops surprising itself with wonder.